Video, we're going to be doing related rates examples involving triangles. This is the third video of my related rates videos, so if you're interested in other related rates problems, I will have those videos linked in the description. So starting with example 1, it says an 8-foot ladder is leaning against a vertical wall. I have a picture for us down below. It does form a right triangle, and we know that it is an 8-foot ladder. That 8 feet is not changing, so I'm going to label that on my picture. The lower end of the ladder is being pulled away from the wall at a rate of 3 feet per second. So I'm going to say X is this distance between the lower end of the ladder and the wall. And it's saying that the lower end is being pulled away from the wall at a rate of 3 feet per second. So I'm going to say we know dx dt is, I'm going to say 3 feet per second. And since the ladder is being pulled away from the wall, dx dt is going to be positive because this length of x is increasing. Then it says when the lower end of the ladder is 5 feet away from the wall, and then letter A, how fast is the ladder sliding down the wall? So we want how fast is the ladder sliding down the wall? Let's make this length y. And if the ladder is sliding down, we're going to want dy dt when the ladder is 5 feet away from the wall. So when x equals 5 feet. So we need to find an equation that relates x and y, and we know that the length of the ladder is 8 feet. So this is going to be a Pythagorean theorem question. X squared plus y squared equals 8 squared. We are going to take the derivative on both sides of the equation with respect to t. We do that with every related rates problem. And we also make sure that we don't plug in anything in the moment. So our 5 feet, we don't do that until after we take the derivative. Now this is going to be implicit differentiation. If you need a video on that, I will link that in the description as well. But this derivative is going to be 2x dx dt plus 2y dy dt. 8 squared on the right side is a constant, so the derivative of that is 0. To make this equation a little bit simpler, I'm going to divide by 2. And I still have 0 on the right side of the equation. Now that I've taken my derivative with respect to t, I can plug in my 5 feet. So I'm going to plug that in for x. This should be a d. dx dt we know is 3 feet per second. Notice that we don't know y. We'll come back to that. I'm solving for dy dt. So as long as I can fill in y, I will be able to solve for dy dt. Now I want y in this moment. So I'm going to draw a side picture. The ladder length is always 8 feet. In the moment, my x is 5, and I want to know what this y value is. So I'm going to do a Pythagorean theorem on this side. I should label this y. I'm going to say y squared plus 5 squared is 8 squared. Y squared equals 64 minus 25, which is 39. So y is the square root of 39 in that moment. So I'm going to plug in the square root of 39. Let's go back to solving our equation. I'm going to have the square root of 39 times dy dt equals negative 15. Divide by the square root of 39 on both sides. Negative 15 over the square root of 39. And let's put our units. That is going to be a length, so feet per second. I should say a rate of a length, feet per second. Notice that your dy dt is negative, and that makes sense because if my top of my ladder is sliding down the wall, my y value is decreasing, so my dy dt should be negative. That is part A. Part B says, how fast is the angle between the ground and the ladder changing? So here's the angle between the ground and the ladder. I'm going to make it theta. And how fast is that angle changing? So I have the same, no, I know that dx dt equals 3 feet per second. And now I want to know how fast theta is changing, so d theta dt. And I want d theta dt at that same moment, so when x equals 5 feet. I know. I do know dy dt from part A, but let's use dx dt. So let's relate x, theta, and this 8. So we're going to have to use my cosine. Cosine is adjacent over hypotenuse in a right triangle. I'm going to say cosine of theta is x over 8. I'm going to take the derivative with respect to t on both sides of the equation. Derivative of cosine is negative sine of theta. D theta dt equals 1 over 8 dx dt. After we take the derivative with respect to t, I can now plug everything in. So I want to know what sine of theta is in that moment. So same thing I did before. I'm going to make a triangle on the side. This is x, this is theta, this is 8. And I should say in that moment, this length is 5. And I want to know sine of theta. We got rad 39 from part A. So sine of theta is opposite over hypotenuse. So rad 39 over 8. So when I'm plugging in, this is going to be negative rad 39 over 8. We're solving for d theta dt. And I know dx dt is 3 feet per second. So let's solve for d theta dt. I have 3 over 8 times negative 8 over the square root of 39. Your 8's cancel. D theta dt equals negative 3 over rad 39. For our units for d theta dt, theta is radians and t is seconds. And that is part B. Part C, I'm going to grab that triangle again. How fast is the area of the triangle formed by the ladder and the two walls changing? So we have the same, no. We know that dx dt is 3 feet per second. And now we want the change in area, so dA dt, at that same moment when x equals 5 feet. So let's do an area of a triangle. Area is x times y times 1/2. Let's take our derivative with respect to time on both sides. On the left side, we have dA dt. On the right side of the equation, I need to do a product rule, x times y, and I'm going to put 1/2 outside that product rule. So I'm going to take the derivative of x, it's dx dt, leave the y, plus leave the x, take the derivative of y, that's going to be dy dt. Once we do the derivative, we can plug in. I'm solving for dA dt, so I'm going to leave that. I have my 1/2. dx dt we know is 3 feet per second. And then we have that same triangle that we've been using now for parts A and B. We know we have 5, rad 39, and 8, and this is x and y. So y in that moment is our rad 39. Our x is 5. And then dy dt, I'm going to pull for part A. We said in that moment, dy dt is negative 15 over the square root of 39. From here, the last thing to do is to simplify. So let's do that. I'm going to start by just multiplying. I have minus 75 over rad 39. Let's get common denominators inside those brackets. I'm going to multiply the first term by rad 39 over rad 39, I should say. We get 3 times 39 over rad 39. And then 3 times 39 is 117. So I'm going to have 117 minus 75. When I do that, I still have my 1/2 out front. 117 minus 75 is 42. And then 42 divided by 2 is 21 over rad 39. This is our dA dt. And our units area is feet squared. Time is seconds. That is part C. We have a couple more problems. Number 2 says 2 cars are riding on 2 different roads that meet at a 90-degree angle. The red car is 4 miles south of the intersection, traveling north at 30 miles per hour. So let's say that this is your intersection. I have a car that is south, and then I'm not an artist, but there's my car. And we're going to say this is the red car. And let's see, it's 4 miles south of the intersection, and it is traveling north 30 miles per hour. So I'm going to make this length x, and I'm going to say we know dx dt. Now notice if the car is traveling north, x is decreasing, so I'm going to make dx dt negative 30 miles per hour. Then it says the blue car is 2 miles east of the intersection. So I'm going to draw another car. And I'm just going to say this is red and this is blue. 2 miles east of the intersection, traveling east 40 miles per hour. So the blue car is going this way. I'm going to make this length y. dy dt. If the blue car is going east, notice that y is increasing. So I'm going to make dy dt positive 40 miles per hour. How fast is the distance between the 2 cars changing at this moment? So in the moment, I'm going to make this green actually. X is 4 miles. Y is 2 miles. And then this is going to be another triangle, a right triangle. Let's make this length z. So I want, how fast is the distance between the 2 cars changing? Our distance between the 2 cars is z. So I want dz dt at the moment when x equals 4 miles and y equals 2 miles. That's what we're solving for. So we're going to use Pythagorean theorem. I want to relate x, y, and z. So x squared plus y squared equals z squared. I'm going to take the derivative with respect to t on both sides of the equation. So I get, similar to the other problem, 2x dx dt plus 2y dy dt equals 2z dz dt. And I'm going to divide by 2 to make it easier. Simpler, I should say. Whoops. X dx dt plus y dy dt equals z dz dt. Once we've taken the derivative, we can plug in. So x is 4, dx dt is negative 30, y is 2, dy dt is 40. And I don't know z in the moment, so I'm going to do Pythagorean theorem, 2 squared plus 4 squared equals z squared. So we get that z squared is 20, so z is the square root of 20. So in the moment, z is the square root of 20 miles. So I'm going to put that in my equation. And we are solving for dz dt, so I'm going to leave that. Let's simplify. Negative 120 plus 80 equals the square root of 20 dz dt. Negative 120 plus 80 is negative 40, and I want to divide by the square root of 20, and that is my dz dt. Let's simplify this. Square root of 20 is going to be 2 rad 5, which is negative 20 over rad 5. I'm going to rationalize. Let's see, stood up here. Negative 20 rad 5 over 5. 20 and 5 cancel. I get negative 4 rad 5. And then for units, we're dz dt, so z is miles, t is hours. And that is our dz dt. One more problem. It says a nighttime jogger is running toward a street lamp at 5 feet per second. So I'm going to draw a street lamp. And a jogger, put him right there, is running toward the street lamp. So I'm going to make this distance x. And I'm going to say we know if he's running towards the street lamp, dx dt, x is decreasing because he's running toward the street lamp. So if he's running toward the street lamp 5 feet per second, dx dt is negative 5 feet per second. The street lamp is 20 feet tall, and that doesn't change, so I'm going to label that on my picture. That's going to be 20 feet tall every time. Jogger is 6 feet tall in his running stance. When he is 4 feet from the base of the lamppost, how fast is his shadow length changing? So I want you to imagine the street lamp is shining light on the person, and so it's creating a shadow on the ground. And we want to know how fast his shadow length is changing. I'm going to make that length s. So I'm going to say we want ds dt, how fast is it changing? At the moment when he is 4 feet from the base. So when x equals 4 feet. And this is our problem. So I like this problem because it makes us use similar triangles, or at least that's how I would solve it. Notice I have a larger triangle. I'm going to make it blue. I'm going to copy it down here. For this right triangle, this leg is going to be x plus s because you have the x and the s. The height of the triangle is 20 feet. And then you have a smaller triangle. I'm going to make it green. I'm going to copy it down here. And this lower leg is s, and then the height of the triangle is 6. So we're going to use similar triangles. You're going to create a proportion. So I'm going to say x plus s over s equals 20 over 6. So this leg over this leg equals height over height. I'm going to simplify this a little bit. I'm going to multiply both sides of the equation by 6 and multiply both sides of the equation by s. And then I'm going to subtract 6s on both sides. I'm going to divide by 2 on both sides. And notice now it's a lot nicer for taking your derivative. So I'm going to take the derivative with respect to t on both sides. We get 3 dx dt equals 7 ds dt. Let's plug in. I know that dx dt is negative 5. I'm solving for ds dt. Notice we didn't need to plug in x equals 4. That's okay. I get negative 15 over 7 is my ds dt. And those units, s is in feet, length of my shadow. T is time, which is seconds. And there's that answer. Notice that your DSDT is negative, so our shadow is getting smaller, which makes sense if you picture the person running towards the lamppost. These are a few examples of related rates problems with triangles. Thank you for watching.